Last video, we looked at what forces were. We sort of introduced this whole section of the course, dynamics, which has to do with forces and what causes motion. Today, we're going to look at some of Newton's laws and get more quantitative and more detailed of how this all comes together. So, to do that, I want you to imagine just pushing a shopping cart, right? You apply a constant force to that shopping cart, and how does that cart move? Now, we spent a whole several weeks of this course describing motion. So when I say how does a cart move, we need to be very specific in what we mean. And what happens is if you have some, shopping cart here and you start pushing it that way, it's going to start from rest, but it's going to start to speed up in that direction, right? So just intuitively from our sort of interactions with the world and all that, we kind of already see that if we apply some force to an object, it's going to cause some sort of acceleration on that object. It's not that it's going to cause it to move with some velocity, but that it's going to actually cause it to speed up in the direction we're pushing it, right? Now, what happens if you fill that shopping cart and it gets a lot heavier, right, at the end of your shopping trip? Well, if you apply the same force, but that cart is much heavier, it's still going to speed up, but it's going to do it much slower. So that acceleration is going to be smaller. So we see that there's some relationship to mass involved with this whole relationship between forces and motion. And it turns out um, that's what we see, right? So you pull on an object or push on an object, apply some force to that object, and what you cause is an acceleration of that object. And this gives us Newton's second law, which is, there's three of Newton's laws we're going to become very familiar with. This, I would say, is probably the most important equation in this course. Essentially, everything we will discuss will come from this equation. But it's that the acceleration of an object is proportional to the total force applied on that object divided by the mass, or the way I prefer to write it is F equals ma, the net force. So the total force of all the forces acting on an object is equal to the mass times the acceleration, right? So on the left-hand side of the equation here, we essentially have the cause, right? You apply a bunch of forces, you have several people pushing on something, all the forces we discussed last video. Maybe there's some tension, a spring, some friction, whatever. If you add up all of those forces to get the total force, that's going to cause it's going to have some effect on the motion. And what that effect is an acceleration um, that relates to the mass. So this is sort of the effect of those forces. And slowly what we're going to build through this section of the course is how to use this and apply it to several situations. We'll look at different situations, look at an object, and on the left-hand side of the equation, we'll develop the skill of being able to analyze what's going on and determine a lot of the forces involved. And we'll look at the right side of the equation and maybe we'll know something about how the object's moving, and we'll put those two together using this equation to answer whatever we need to know. So that's Newton's second law. F net equals ma. Again, it's hard to overemphasize how important this equation is for the course. This gives us one of a very important situation that we often see, where what happens if there is no net force? So you're probably sitting still on your chair right now with no total force acting on you. So if we are in a situation where F net is equal to zero, what happens? Well, we're in what's called mechanical equilibrium, right? If you think about that word equilibrium, maybe you've heard it in other courses. If there's chemists or chemistry majors watching, you use chemical equilibrium a lot. And what that is describing is essentially you have some reaction, and the rate of forward reaction is the same as the rate of backwards reaction, and you have an equilibrium situation where the average concentrations of the different elements or parts of that reaction stay constant. Equilibrium essentially is describing that balance of the two sides, right? The forward and the backwards. It's the same sort of thing in physics. Equilibrium is describing a balance, right? Those forces balance. For every force kind of pushing to the right, there's a force pushing to the left and they balance, making that net force zero. And when that happens, we have acceleration is equal to zero because of, F equals ma, Newton's second law. And this is a very common situation, right? There are two, we split this up into two sort of types of equilibrium. One we call static equilibrium, which is when your velocity is also zero. So again, right now you're probably watching this video sitting down and not moving. Your velocity is zero. You're not accelerating. So you are in static equilibrium. And just from the fact that we know your acceleration zero, we also know that your net force is zero, right? If you know F net is zero, you know the acceleration must be zero, and vice versa. The other type of equilibrium is dynamic equilibrium, which is if you're moving, but you're moving at a constant velocity, so your acceleration is zero, the net force is also going to be zero, right? That again, F net is equal to ma. That is going to be true. So if you're moving at a constant velocity, so same direction, same speed, you know your net force is zero. That's called dynamic equilibrium. Dynamic because you're actually moving, but still equilibrium because your acceleration and your force are both still zero. An important thing that we have to remember, though, is all of these quantities, velocity, acceleration, forces, they are vectors. So the direction does also matter in this. But anyway, equilibrium is kind of brings us to Newton's first law. Newton's first law, you've probably all heard it or paraphrased as an object at rest stays at rest, an object in motion stays in motion. More detailed, there's the textbook sort of the way the textbook words it there, but the idea is an object without any net force acting on it stays in uniform motion. So if you remember way back when we first started discussing kinematics and how things move, we described uniform motion as an object moving in a straight line with a constant velocity. And the reason that we gave that situation a name, uniform motion, is because that's the natural state of an object, right? And when Newton came up with his three laws, and that this was kind of a new thing, right? If you think about it, a lot of what we see, things tend to stop, right? If you throw something, eventually it will slow down and stop. Almost everything comes to a stop. So philosophers and that used to think that that was sort of the natural state of things. It turns out that's not true. The natural state of some object in the universe is to just maintain that constant velocity, same speed in a straight line, unless there is some force being applied on it by some other object, some net force. So this is Newton's law of inertia. It kind of describes what a force is and what it does. Newton's second law is the equation that kind of allows us to analyze those forces. So those are Newton's first laws, and they may seem straightforward, but as we'll see throughout this course, the amount of things that we can derive and figure out using those things, these ideas, is pretty remarkable. So the next thing we need to do is, now that we have sort of our axioms or our base things we're going to start from, F equals ma and what forces are, we want to be able to start analyzing situations. And one of the most important skills we're going to have for this is drawing a free body diagram, right? In the last video, we looked at how to identify forces, and that's the first step in this drawing a free body diagram. Identify all the forces we care about. The second step, draw a coordinate system. Again, forces are vectors, so we're going to need to include the direction in that. So a coordinate system to describe it is important. We're going to represent the object in the particle model, so we're going to draw the object. And then we're going to draw all the forces that we identified in step one on that free body diagram. And then at the end, we want to include whether we know that the net force is zero, or add up all those vectors. And that will give us a nice visual representation of the forces in our system that are relevant to what the object we're thinking about, and set up a nice sort of model that we can apply Newton's second law to. probably best to just do an example of this so we can see how it all works. All right, so here's the situation. Your car runs out of gas and you have to push to the nearest gas station. You're pushing it up a hill at a constant speed, right? So if you recall how to identify forces, that was the first thing we had to do. Step one, ID the forces that are involved in the problem, right? So how do we identify forces? First, we need to think about what object we're looking at. In this case, the car. The next thing is draw a picture of it, and then circle the car. So I've circled the car. I know the object I'm talking about. Next thing in identifying the forces, what breaks that circle? What crosses through that? And you can see, well, there's the surface of the road. So that's something that is touching my object, my car. So what contact forces can surfaces exert? Well, there's a normal force and possibly a friction force, right? What else is touching this car? Well, the only other thing touching the car is the people pushing it, right? So what type of force is that? We'll just call it FP, some force of the push. You push it in some direction, right? Is there anything else breaking that circle I've drawn around my object? No. So I've identified the only possible contact forces because those are the only things touching my object. I've identified three of them. Those are the only ones I have to concern myself with. The last step of identifying forces is, well, are there any long range forces? And we're on Earth, so I have to concern myself with that gravitational force, right? So I've identified the four forces I'm concerned with. The next step is draw the free body diagram using those forces. The first step in drawing a free body diagram is we kind of need to have a coordinate system. You can switch the order of these steps. I prefer to draw a coordinate system after I've drawn the forces. You can do whatever you like, but the gist is here's my object. Oops, sorry. Here's I'm going to use a particle model. There is my car. I like to draw a line or something that aligns, since this hill is on a slope. I like to sort of include that slope in my free body diagram just to orient myself. And then the next thing, include all these forces, right? So, let's just go through them. Gravity. What direction is gravity in? Well, we learned in the last video, gravity points straight down towards the center of the Earth. So gravity points that way. What about the force of the push? Well, the force of the push, sorry again, you're trying to move the car, so you're going to push it up the hill, right? And label that as force of the push. The last two forces are normal and friction. We learned that the normal force is always perpendicular to the surface that's applying that force, right? So this is one of the reasons why I draw this line here as my slope. So that normal force is perpendicular to that, and friction is always parallel to that surface. And in this case, since the car is moving at a constant velocity, it's moving along that surface, that friction force is going to oppose that in the opposite direction, be in the opposite direction of that motion. So that friction force is, I drew that a little large. The friction force is going to be something like that, right? So I've drawn all four of my forces on this free body diagram, and that's a really excellent start. I know I've got all four because I identified them carefully. I know the directions they're in from what we learned last video about the types of forces. The last thing is, well, sorry, I forgot one thing is we're also going, let me do this in red, we're going to want to have a coordinate system. And in this case, you're kind of free to choose it. The only restriction on our coordinate system is we need, an X and a Y direction, and they need to be at a right angle to each other. But we can make our lives a lot simpler if we choose a convenient direction for them. For now, I'll just say this briefly. The probably most convenient direction, the most convenient directions for this would be have X be along the surface of the road and Y be perpendicular to the surface of the road. And the reasoning behind that is, if you think about this, ultimately we're going to be using Newton's second law, F net equals mass times acceleration. And this is a vector equation, right? So we're going to have to, right here, we're doing vector addition. We're adding all these forces together. To add vectors, we break them into components and add their components, right? So we're going to have to break all four of these vectors into components. If we align our coordinate system this way, they're aligned, three of these vectors are aligned in a way that doesn't require any breaking down of components. The push is all in the x direction. Normal force, all in the y direction. Friction, all in the negative x direction. The only force we'd have to break down into components and do some trig with is g, the force due to gravity. So it's not that this is the only way to do the problem, it just makes the math much less tedious. We have a lot less trig to do just by making this choice of coordinate system. Had we chosen, an x and a y direction in our standard left, right, up, down, all three of these, normal force, friction force, and push would have to, x is sine theta or cosine theta, or, we'd have to figure out all those angles, do all that trig. We can do it, but it takes a lot more effort. So anyway, back to the actual free body diagram. We've got it set up. The last thing we need to do is acknowledge that we're moving at a constant speed, right? So if we're pushing the car at a constant speed, we know that our net force has to be zero. I've tried to be sort of careful about that with this, but my vectors probably aren't exactly to scale. But the gist is all of these have to balance to zero. We know F net is equal to zero because our acceleration was zero. So all of these have to balance. And if we look at this, if I were to break this gravity into components, right, this side, this component of gravity does seem to balance that normal force. So the force in our y direction does appear to be zero. And then if I take this force of friction and this x component of gravity and add them together, it's roughly the same size as that force due to the push. So the force in the x direction also cancels. And we are getting F net equals zero. But point being, I've kind of, gone over detailed in this, I think. We want to get very good and proficient at drawing these free body diagrams. I would say well over 90% of the time when students come with some difficulty in a dynamics problem with force, so I'm having trouble getting this answer, what am I doing wrong? We just go back to their free body diagram, and either they have a force in the wrong direction, they're missing a force, there's something in this process that's gone wrong. Because after this, really, it's just this vector math. How do we add up all those forces and break it down into components? But the physics, most of it's right here in drawing that free body diagram. So in our synchronous sessions and in our homeworks, we're going to be practicing this a lot. Be sure you discuss it with me and talk to me about any difficulties so we can fix them. Because this, again, is one of the most important skills we're going to have in this course, really, but especially this section of the course to help analyze all these situations. All right, the last thing I want to mention briefly is this thought experiment. I'm just going to first pose a question, and it'll get us into a sort of interesting topic. But let's say you're standing on a train or a bus or even a plane, whatever. You're in some vehicle that's driving and moving along at a constant speed. All of a sudden, that train slams on the brakes, right, and stops. And you were just standing in the aisle. You get thrown forward in the train, right, and you just start accelerating forward in that train and end up, falling forward onto your face. Hopefully, you're okay. But so you've clearly accelerated in that train. What force causes you to accelerate? Now, pause the video, think about it for a minute, see if you can come up with an answer. All right, I'm going to assume you did that. The the gist of that answer is, if you look at how we think about forces, so if I were to draw, here's the train car, here's me standing in it. If I circle myself, right, and I'm moving at some constant velocity, what forces can be acting on me? Well, I have some friction and I have some normal force because I'm touching the surface of the train and the long range force of gravity, right? So if I just look at forces acting on me, essentially I have normal force and gravity and possibly some friction in the left or right direction, right? Um, but it seems, we know that if I'm in the train, it feels like I accelerated forward that way. So that would kind of argue that this friction force must be forward. But that doesn't really make sense to me. The train didn't all of a sudden push you forward from the ground. So how do we sort of resolve this? It doesn't seem to be making sense here. And the answer is you're not actually accelerating, right? So this friction force is you know is not pushing you forward, right? So that's not there. Your up and down force is balanced in equilibrium. The real answer is we're not really accelerating, right? That train is slowing down and the train is accelerating that way. We, if I were to draw a thing, are just continuing forward at an acceleration equal to zero, or a velocity equal to that constant velocity, right? So the feeling that you have of falling forward isn't you accelerating forward. It's you in uniform motion, obeying Newton's first law and going at a constant velocity, while the train accelerates backwards. And why it's important to sort of make this difference is what we've sort of seen here when we tried to analyze, our free body diagram and our motion in that is this is telling that Newton's laws don't work if you were to measure the velocity, if you were measuring things from the train, right? If you were sitting in a train and you see it and it stops and you're sitting down with your seatbelt on and you see someone fall in the aisle forward, it looks like they accelerated. You would have measured some acceleration on them, but you wouldn't have seen any force. You wouldn't have been able to infer some force pushing them. So it looks like you just saw that mass force does not equal mass times acceleration. But the reason that doesn't work is because you were measuring that situation or observing that situation from what's called a non-inertial reference frame, which means uh, an inertial reference frame is defined essentially as a reference frame where Newton's first law is true. Um, Basically, if you're accelerating, you can't use Newton's laws the way we've written them. Your acceleration would screw up any measurements you made of that system. If we were to actually observe that person from outside the train, uh, you would see them continue on forward with that constant velocity. If you analyze the forces, you would see that the net forces are all balanced, and we would get agreement with Newton's second law. So this is just a sort of a subtle point. We're not going to spend a whole bunch of time discussing it, but I think it's very important that you're aware of it, that Newton's laws apply in inertial reference frames. So that's essentially it for today, right? So what we've covered is Newton's first and second law. The second law being the big equation F net equals ma, where the forces all add up to equal the total force, the net force, and all of these forces are going to cause an acceleration on whatever object we're talking about. Newton's first law was an object in motion stays in motion at a constant velocity in a straight line unless some net force is acting on it. An object at rest stays at rest. We talked about equilibrium. And one of the big things we've really started doing is we've started to lay the groundwork of how we're going to develop models and analyze situations. And so far, what we've got is the first step that we kind of covered in the last lecture was to identify the forces involved in our problem. So this was, pick the object we're trying to describe, circle it, identify the contact forces and the long range forces, and make sure we're including everything that we need to include in our analysis of this problem. The second is to draw our free body diagrams. This is what we what we discussed today, um, where essentially we're going to, use our particle model and then making sure we include all the forces from step one. There may be a normal force or gravity, maybe some tension, friction perhaps, or whatever other forces there are, something pushing it. All the forces that we're concerned, we're going to draw them in some way in our free body diagram. Step three, I like to write as a separate step, but we want to include a coordinate system. So we're going to define some coordinate in that free body diagram. So who knows, whatever, something, we have a y direction in the upwards direction and x left to right. And this is going to allow us to break that equation into components. It's a vector equation. So we're going to want x and y components of all these vectors so we can add them together. And then the final step that we're going to get to in upcoming lectures is we're going to apply F net equals ma to this free body diagram we've got and take all the information we know from the problem. Again, the left side of the equation is everything we can get from just sort of analyzing the forces involved, and the right hand side of the equation is sort of the effect of the on motion that is caused by those forces. And perhaps we know something about how the object's moving, and from everything we've done up to date in this course, if we could perhaps identify an acceleration, we can plug that in there. But this sort of strategy is going to come up repeatedly in upcoming lectures. The next few, we're going to start to look at this final step and how we can actually quantitatively calculate some of these forces. Like, what is the force of gravity equal to numerically? Or how can we treat and model friction? So that's upcoming lectures. Again, if you have, as always, if you have any questions or concerns, please reach out to me either email or in our synchronous meetings, and we will deal with them.